Hello there. In this lesson, we're going to do round 2 of VSEPR Theory, and we're going to address all the different molecules that have the valence shell expansion. So our SP3D and our SP3D2 varieties. And then when we're done that, we're going to look at predicting the dipoles on a molecule and being able to tell whether or not it'll be polar. So let's get started. So when you expand into the D subshell, SP3D hybrid molecules will have 5 pairs of electrons around the central atom. And so you end up with this one up, one down, sort of 180 degrees from each other, and then one at 90 degrees from those two, and then 2 more on that same plane that are 120 degrees from each other. And then for the SP3D2 variety, you end up with kind of like jacks. If you ever played jacks, they got the same sort of basic shape where everything is 90 degrees from each other. All right, so when we're going to make our molecular shapes, we're going to leave out the lone pairs, even though they help with the overall shape of the molecule, right? Molecular shapes don't have lone pairs. Okay, so let's look at the first one. So SP3D hybrids. First off, we've got PCl5, and that is an example of one that doesn't have any lone pairs. If we have 5 bonded chlorines around here, you're going to put one up, one to the side, one straight down. So all of those are 90 degrees from each other. And then one out here at 120 degrees from the other middle chlorine, and one back away into the screen, which would also be 120. So these angles here are all 120 degrees, and then the up and down ones are both 90. Our second one here is sulfur with 4 fluorines, which is also a SP3D hybrid. So you're going to have the same 4 fluorines in different spots, and then one lone pair, usually around the middle is where you put it. Now the way I've drawn it is kind of hard to see, but sometimes they call this seesaw. Maybe if I did it on its side, you'd be able to see it better. So if you put the 2 fluorines that are opposite each other that way, and shoot one fluorine straight out, and one fluorine going back away, and then make this your lone pair, it does kind of look like a seesaw. If you sit someone on here, hello, hold on to the seesaw, someone over here, there we go, hello, hold on to the seesaw, and then they can go up and down. It also kind of looks like an alien who's coming in to get a hug. So there you go. 2 more SP3D hybrids that include lone pairs. If we have 2 lone pairs, you can make what's called T-shaped. So we got a chlorine in the middle here, and then we got 3 fluorines. So if we put 2 opposite each other, and of course the dots on it, and then one straight down, you can see it makes, the letter T there. And then you have 2 lone pairs that are also around the middle, and so it's kind of like a one-legged alien with 2 heads that's coming in for a hug. But T-shape is the usual name they give that, because again, we're just going to where the bonds are, right? This last one that we have down here is xenon with 2 fluorines on it. So you got xenon, and it's going to have 3 lone pairs around the middle. So we're going to have 1 fluorine up and 1 fluorine down, again with the valence shell expansion. And then all 3 of the lone pairs will be around the middle here. Lone pairs always end up around the middle. And so because all 3 of these are all in one line, this is considered to be a linear shape. Alrighty, so let's look at our SP3D2 hybrids. This time we're going to have the sulfur in the middle. We've got 1 fluorine up, we got 1 fluorine down, and then usually you show them 2 of them coming out at you on either side, and then 2 going back away. And then of course we would put in all of our valence electrons as well for the rest of the fluorines, just so that we're being thorough. And there you go. So that's called octahedral. Can't really see it the way it is, but if you use your imagination, imagine strings going down to each one of these things. You would end up with a four-sided pyramid on the top, and then a four-sided pyramid on the bottom. And so that makes 8 sides, and that's where the octa comes from for octahedral. 2 more variations for our SP3D hybrids. We got a bromine here with 5 fluorines on it. So we'll put one up here, put one coming out, put another one coming out over here. Ooh, I'm getting sloppier. Slow down, Mr. K. There we go. So I'll put them all like so. And they'll only stay that way if we include the lone pair, which doesn't really matter where you put it, but you can always twist it around so that the lone pair is at the bottom. And if you do that, you've got a pyramid with a square base. So if you're looking at the shape of it, it's got a square at the bottom here, and they all go up to the fluorine at the top. And you call that a square base pyramid. The second one here, of course, is a xenon with 4 fluorines. So you're going to put all of those around the middle. And that is so that those lone pairs, which repel a little bit more than bond pairs, can be opposite to each other. And so you end up with a lone pair up here and a lone pair down here. And the shape of this guy ends up being just square and flat. And the fancy word for flat is planar. So square planar for that one. Oh, I forgot my extra electrons. Better finish it up, make it look pretty. There we go. Lovely. All right, so let's predict some shapes here. So we got iodine and 3 fluorines. So if you're not sure, you're just starting, it's good to draw out the Lewis structure first. And so you put your iodine down, and you got 1, 2, 3, 4, 5, 6, 7, and you got 3 fluorines. So you put fluorine here, and then you're going to have to promote one of these. And you're going to put 3 fluorines and 2 lone pairs. You're like, what can I do with that? Well, that would most likely give you, because it has an SP3D shape with 1 lone pair, that's going to be our T shape, right? So you put the iodine down, put the 2 fluorines out to the side, 1 to the bottom, and you got your 2 lone pairs up here, and you say T shape. Yay. So PF3, so again, Lewis structure first, 1, 2, 3, 4, 5. Going to stick on 3 fluorines. And you're like, that's an SP3 shape. Kind of looks like ammonia. So for our molecular shape, we're going to call that one out and one kind of back. We'll call that trigonal pyramidal. Oh, pyramidal. Oh, my table's creaking a bit. Yeah, so then the next one here we have is a chlorine, and chlorine has 7 valence electrons, and we're going to bond with 5 of them. So we got fluorine, 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 fluorine. Great, so 5 bonds, 1 lone pair. I think the only one that works for that is going to be an SP3D, 1, 2, 3, 4, D2. So we need to have 1 lone pair. We'll put that at the bottom. And we're going to put our chlorine here and then fluorines all around it. And our shape for this molecule is going to be the square-based pyramid. Square-based pyramid. You'll have a reference sheet to start with to look on and see which one matches to begin with. But eventually you'll get to know them all. There's not that many. And you'll be able to assign any molecule to its shape. Now we have a carbon here with an oxygen and 2 fluorines, right? So this is going to be an S and P2 because there's 3 bond pairs there. And so that's going to give us our 120 degree sort of triangle shape. And we call this trigonal planar. It's a flat triangle. There you go, everybody. I hope that you learned some. Oh, wait a second. We're not done. Polarity. How could I forget about polarity? The whole reason why we were working out all these shapes is to be able to decide whether a molecule is going to be polar or not. If you remember way back in the beginning there, we were learning about polar molecules due to the electronegativity difference between the elements that are bonded. And we learned that the most electronegative element is going to have a slight negative charge, while the lesser one would be the slight positive charge. And you end up with these things called dipoles. And so for oxygen and hydrogen, oxygen is more electronegative, and so there'd be a dipole there. And also with the other one on the other side. So we'd have these two dipoles. And then the question is, does that make a polar molecule? Well, polar molecules are the result of dipoles that produce positive and negative sides of the molecule. So it have to have an asymmetrical shape in order for that to happen. And so water does. You see that both of these dipoles are pointing towards the oxygen, which means this oxygen is going to have a slight negative charge. And the places where the hydrogens are is going to have this slight positive charge. So overall, if we put the total dipole, it's going to be something like this, where it's pointing from a positive side on the hydrogen end here, positive over here, and a slight negative on this side, right? So that's called the net dipole, which is the combination of all the little dipoles inside of a molecule. It's the net dipole. And when there's a net dipole, that means that it's a polar molecule. So if the two or more dipoles that you have don't cancel each other out, then you'll end up with a net dipole, and that makes a polar molecule. If you're good at math and you've learned about vector addition, the dipoles work like vectors. So if you add up and you get a net dipole, a net vector overall, that means you got a polar molecule. If they all cancel out and you have a net vector of 0, well then there's no dipole. So let's look at a few that don't have an overall dipole. Oxygen is more electronegative than carbon, so the dipole for that bond would go this way. But you have another oxygen in the exact opposite direction. And so what happens is that these all get canceled out. And so overall there's no net dipole because the dipoles are in equal but opposite direction and they cancel. Same thing with a tetrahedral shape. Basically, all of the molecules that are lacking lone pairs will all spread out, and you'll have the net dipole being 0 because they'll all cancel out. So fluorine, if you remember, is the most electronegative on the table. So we definitely have individual dipoles for each of these bonds. But because they all are equal but in opposite directions from each other, the overall dipole for this whole thing is again 0. 0 net dipole. And that means non-polar. Alrighty, so let's put it all together. We have 3 nice VSEPR shapes here drawn out, and we have to decide whether or not these are going to be polar or not. So we know fluorine is most polar or most electronegative between it and sulfur, and so we're going to get dipoles going this way and that way to wherever the fluorines are. So we can see that the 2 fluorines on the side, they do cancel each other out, right? So this guy and this guy cancel out, but there's nothing to cancel out the fluorine electronegativity difference going downwards here. So the net dipole for these guys is going to be the sulfur will have the slight positive charge, and the side with the fluorines will have the slight negative charge. And so this is going to be a polar molecule. We have phosphorus pentafluoride here. All right, so again, we've got dipoles sticking out everywhere towards these fluorines that are attracting all these electrons from the shared pairs. But these 2 cancel each other out, and these 3 all cancel each other out, so that means no net dipole. And that means, therefore, non-polar. Finally, good old PCl3. I think chlorine is slightly more electronegative. Oh, I need my red back. Slightly more electronegative than the phosphorus. And so we'll aim all these out towards there. Remember again, the lone pairs don't have dipoles because there's no other atom there to attract electrons. And what we see here is that there is some cancellation. The all pulling away from the center would cancel, but the up and down is not canceled. So there's going to be a slight dipole here downwards because all of these chlorines are all kind of bent down away from that lone pair at the top. And so that would make it a slight net dipole, so it means slightly polar. And so this side down here would be a little bit negative, and the phosphorus up here would be a little bit positive. So polar for this last one. All right, hope that helped. We'll see you soon.